Before we get started today, let me talk about the miracles of white balance. So if you look in these settings that I use for recording these videos, I usually just let it do the automatic white balance. And if you do that, I'm ghostly. Look, I'm all ghostly. I guess maybe it's arguably, it's not really how the room feels. I think it's more just the reflection of the monitor. So anyway, I changed it up. So now we're gonna live a richer, warmer life, and I hope you like it better. Anyway, let me know what you think. So continuing along, let's talk about 2-3 trees and 2-3-4 trees. So last time we saw these really nice, beautiful, automatically balancing trees called 2-3 trees, or B trees more generally, and it turns out that while they're great, they're a really big pain to implement. And if you actually implement them, they're just not as fast as other alternatives. They're theta log n, but there's better theta log n's out there. So some of the issues that cause 2-3 trees to be complex and a little bit slow is having to keep track of different node types, 2 nodes, 3 nodes, temporary 4 nodes, the need to interconvert between node types, and the need to walk up trees to do splitting of nodes. So to get some flavor for what a 2-3 or a 2-3-4 tree implementation might look like, here is a fantasy 2-3 code implementation that I got from Kevin Wayne, my former teaching mentor at Princeton. And here we see that it's kind of messy, right? We have this strange function where we have to walk up the tree, split nodes, take 2 nodes, make them into 3 nodes, and so forth. And I think we can summarize the issue here with this really nice Knuth quote, which is that beautiful algorithms are, unfortunately, not always the most useful. So what we're going to do today is we're going to walk through a totally different way of doing things that's inspired by a 2-3 tree, but which will ultimately be simpler and faster. Our new way of balancing trees is going to be fundamentally based on an operation known as tree rotation. Now, before we get to what that operation is, let's talk about the space of all possible binary search trees. So let's say we insert the items 1, 2, and 3 into an initially empty binary search tree. Well, if we do 1, then 2, then 3, we get the configuration shown on the far left. If we do 2, followed by 1, followed by 3, we would get this bushy tree in the middle. And it turns out there are 5 different binary search trees that can contain these 3 numbers. And the specific binary search tree that you end up with is based on the order that you insert. Now, more generally, once we get up to, say, 4 items, we'll have many more possible trees, different configurations that can exist. I think for 4, the number is 14. And more generally, there's a function or a series of numbers known as the Catalan numbers that describe the number of different binary search trees. Now, we're not going to talk about that in this class at all, but I put a link here in case you're curious. And it's kind of neat because in CS theory, you'll see that the Catalan numbers pop up a lot because many different recursive data structures that are out there that are possible, if you enumerate their states, you'll see that the Catalan numbers seem to appear. So if that seems kind of cool to you, check it out. Now, given any binary search tree, there is an operation known as rotation, which I'll describe in a moment, that lets you move between states. That lets you say, I currently have this tree, and I want this one instead. And the rotation process will still preserve the search tree property. These are all valid binary search trees, but rotation lets you move between the states. And yet more importantly, in general, we can move from any configuration to any other. So if we have a tree that is really, really unbalanced, there exists a sequence of rotations that'll get us to a bushy state. And we can show, we won't in this class, but it takes no more than 2n minus 6 rotations for sufficiently large n, I think for n greater than 11, something like that, from an old Bob Tarjan paper that you can read here, or a Medium post that summarizes a paper that's very nice. I recommend this. It's pretty cool if you think this seems interesting, by Amy Liu. But that's kind of setting the stage. So there exists a rotation operation that lets us move between possible binary search tree states. So what is rotation? Well, the idea is we pick a specific node, and we either rotate it to the left or to the right. So I'll give an example of rotating to the left. So let's say I'm rotating G to the left. Well, we'll define X to be the right child of G, in this case P, and then we're going to change the tree so that G is the new left child of P. Okay, so let's try that out. So I'm going to take this graph, or this tree, sorry, and I am going to change it so that G is the new left child of P. Okay, so I'm starting the process. Okay, so there we go. G is now the left child of P, but I'm not done yet because right now P has two children. That doesn't really make sense. So since G is P's left child, I need to do something with K. K could no longer also be the left child of P. I'll notice that G is also missing a right child because, well, the right child used to be P. So I'm going to take this link and move it over here, and that is the rotation process. Now there's an alternate way of thinking about the rotation process, which is it is essentially like temporarily merging G and P and then sending G down and to the left. So in this case, we think of them as merging together, and then G goes down and to the left. And in this case, the rotate left operation increased the height of the tree. We went from a height 3 tree to something that's a little less bushy, that is height 4. Okay? Now again, it's really important to notice here that there's no change to the semantics of the tree. It still means the exact same thing. It is a binary search tree containing A, B, C, G, J, K, L, P, R. Right? Both of these are valid binary search trees that do that thing, but they're two different versions. So now to test and make sure that this makes sense, I would like you to try and rotate P to the right. Okay? And you could think of it as temporary merging or not, however you want to do it. So maybe pause the video and figure out what the tree should look like after. It's a noisy dog. I don't know if you can hear it, but I can hear it. All right, so after we rotate P to the right, what we end up with is the tree shown here. So in this case, we actually just undid the previous rotation. And here, the rotate right operation, it decreased the height of the tree. Okay, so hopefully now you understand the basic idea for what rotation is, and in the next video, we'll see in great detail why it is useful.